Solving for hypotenuse and base in practical scenarios. Welcome, everyone. Before we dive into today's new material, let's take a moment to reflect on what we have already mastered. In our previous lessons, we focused primarily on using the tangent ratio, that is, tan theta, to calculate the vertical height of an object or the horizontal distance from its base. This was very useful for finding how tall a tree is or how far away a building stands. However, as we move into more complex, real-world applications, you will find that we aren't always just looking for vertical heights or horizontal distances. Often, we need to find the length of a slanted path, like a ramp, or the direct distance between 2 points across a diagonal, such as the length of a kite string. Because these scenarios involve the longest side of the triangle, we cannot rely on tangent alone. In these specific instances, we must expand our toolkit and learn to utilize the sine and cosine trigonometric ratios to find our answers accurately. Let's look at how to choose between them in the next slide. Understanding the selection of ratios. To determine which trigonometric ratio to use, you shouldn't just guess. Instead, you must first identify which two sides of your right-angled triangle are involved in the problem. Specifically, you need to look at the side you already know and the side you are trying to find. First, use the sine ratio. You will use sine when the problem involves the opposite side, which we often think of as the vertical height, and the hypotenuse, which is that slanted length we discussed in the previous slide. Mathematically, we express this as sine theta equals the ratio of the opposite side over the hypotenuse. On the other hand, use the cosine ratio. You will use cosine when the problem involves the adjacent side, which represents the horizontal base distance, and the hypotenuse, or the slanted length. We write this as cosine theta equals the ratio of the adjacent side over the hypotenuse. Now that we've established that we are moving beyond just using tangent, let's look at how to actually choose the right tool for the job. There are two main paths you can take here. Keep these two pairings in mind, because in the next slide, we are going to apply this exact logic to solve a practical problem involving a ladder. Finding the hypotenuse, the slanted length. A very common real-world scenario for finding the hypotenuse, which, as we discussed, is that slanted length, is determining the length of a ladder leaning against a wall, or perhaps the length of a ramp. Let's look at this specific example, calculating the length of a ladder. Imagine a ladder is leaning against a vertical wall. The foot of the ladder is resting on the ground, and the top of the ladder reaches a window at a height of 5 meters from the ground. The ladder makes an angle of 60 degrees with the ground. Our goal is to find the total length of the ladder. Let's walk through the step-by-step solution together. First, we need to identify our given values. Looking at our triangle, the height of the wall represents our opposite side, which is 5 meters. The angle of elevation, theta, is 60 degrees. The length of the ladder is our hypotenuse, which we will call BC, and this is the value we need to find. Second, we must select the appropriate ratio. Recalling our selection guide from the previous slide, since we have the opposite side and we are looking for the hypotenuse, the sine ratio is our best tool. We use sine theta equals opposite over hypotenuse. Third, we substitute our known values into this formula. This gives us sine 60 degrees equals 5 over BC. Fourth, we need to rearrange the equation to isolate BC to do this. We multiply both sides by BC and divide by sine 60 degrees, which leaves us with BC equals 5 divided by sine 60 degrees. Fifth, let's substitute the exact trigonometric value. We know that sine 60 degrees is equal to the square root of 3 over 2. So our equation becomes BC equals 5 divided by the fraction, square root of 3 over 2. When we multiply by the reciprocal, we get BC equals 10 over the square root of 3 meters. Finally, for the final calculation, if we choose to rationalize the denominator, we get BC equals 10 root 3 over 3 meters. This calculates to approximately 5.77 meters. Now that we understand how to choose between sine and cosine from our previous slide, let's put that theory into practice. This result makes sense, as the hypotenuse should be longer than our vertical height of 5 meters. In our next slide, we will see how a similar process works when we are looking for the horizontal base instead. Finding the base, the horizontal distance. Now that we have mastered finding the length of the hypotenuse using the sine ratio, let's shift our focus. In our previous example with the ladder, we were looking for that slanted length. But what if we already know the length of the diagonal, and we actually need to find the horizontal distance along the ground? A perfect real-world scenario for this is looking at a kite flying in the sky. Imagine the kite string is stretched tight, forming a straight line. Let's look at this specific example. A kite is flying at a certain height, and the string is pulled taut. We know the length of the string is 100 meters, and it makes an angle of 30 degrees with the horizontal ground. Our goal is to find the horizontal distance from the person holding the string to the point on the ground directly underneath the kite. Let's walk through the solution step by step. First, we must identify our known values. The length of the string represents our hypotenuse, which is 100 meters. The angle of elevation, which we call theta, is 30 degrees. The value we are trying to find is the horizontal distance, which we will label as x in our triangle. This x represents the adjacent side. Second, we need to select the correct trigonometric ratio. If you recall from our previous slide, we use sine for opposite and hypotenuse, and cosine for adjacent and hypotenuse. Since we are working with the hypotenuse and the adjacent side, we must use the cosine ratio. That is, cosine of theta equals adjacent over hypotenuse. Third, let's substitute our known values into this formula. This gives us cosine of 30 degrees equals x over 100. Fourth, we need to rearrange the equation to isolate x. To do this, we multiply both sides by 100, which leaves us with x equals 100 times cosine of 30 degrees. Fifth, let's substitute the actual trigonometric value. We know that cosine of 30 degrees is equal to the square root of 3 over 2. So, our equation becomes x equals 100 times the square root of 3 over 2. Finally, we perform the calculation. 100 divided by 2 is 50, so we are left with 50 times the square root of 3. When you calculate this out, it comes to approximately 86.6 meters. So, the person is standing 86.6 meters away from the point directly under the kite. As we move to the next slide, we will summarize these key takeaways to ensure you can distinguish between these ratios every time. Key takeaways. First, remember that the hypotenuse is always the longest side of your right-angled triangle, and it is always positioned directly opposite the right angle. When you are looking at practical problems, think of the hypotenuse as that slanted path. Like the ladder leaning against the wall we calculated earlier, the kite string in our second example, or even a playground slide. Next, let's refine our strategy for choosing the right ratio. If your problem involves the vertical height and that slanted length, then sine theta is your tool of choice. Conversely, if you are dealing with the horizontal distance along the ground and the slanted length, then cosine theta is the ratio you should use. Finally, I cannot stress this enough. Always start by drawing a rough diagram of the scenario. By sketching the triangle, you can clearly and correctly identify which side is the opposite, which is the adjacent, and which is the hypotenuse relative to your given angle. This simple step will prevent many of the common mistakes we are about to discuss in the next slide. All right, let's take a moment to recap everything we have covered in this lesson so that you have a clear summary to take away. Common mistakes. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. Even if you understand the formulas, it is very easy to make small errors that can lead to the wrong answer. Let's look at these common mistakes so you can avoid them in your exams. First, a very frequent error is the habit of using tangent for every single problem. Because we spent so much time using tangent to find heights in our previous lessons, it becomes a reflex. However, as we saw in the examples with the ladder and the kite string, if the problem involves the slanted side, the hypotenuse, you simply cannot use tangent. Remember, tangent only relates the two legs of the triangle, the opposite and the adjacent, and ignores the hypotenuse entirely. Second, watch out for incorrect side identification. It is incredibly easy to confuse the adjacent side with the opposite side. A helpful tip to keep in mind is that the adjacent side is the one that physically touches your given angle theta, but is not the hypotenuse. Always double-check your labels before you start calculating. Third, be careful with algebraic errors during rearrangement. This often happens when your unknown variable, like x, is sitting in the denominator. For example, in the equation sign theta equals opposite over x, you must be very disciplined with your algebra to ensure you multiply and divide correctly to isolate x on one side of the equation. Finally, do not mix up your sine and cosine values. It is easy to get these scrambled during a stressful exam. For instance, make sure you don't accidentally use sine 30 degrees equals 0.5 when you actually need cosine 30 degrees, which is the square root of 3 over 2. If you stay mindful of these 4 points, you will be well on your way to mastering these practical trigonometric applications. Great job today!